We also have things that are called an upper sum and a lower sum. They're a little more complicated than the left and right hand points. To use the upper sum, you use the point which gives the lowest value as your representative. And the reason you would do that is that the sum you'll end up with is an underestimate. This is what we were doing when we worked out this function. The thing we did was a left-hand endpoint sum to get the minimum, but because the function was increasing, that left endpoint of our interval was the lowest value the function takes on that subinterval. And because we always had a value that was lower than all other values, we wound up with an underestimate of the interval. And for an I screwed this up. The lower sum is the point which gives the lowest value. The upper sum is the point which gives the highest value. So for the upper sum, you use the point with the highest value. And this gives an overestimate of the integral. Let's try this out. Let's do an example. Oh, come on. Let's estimate the integral from 1 to 5 of 1 over x squared dx. Oh, actually, we should talk about this notation before we do an example of estimating. So the way we write an integral, so the integral we computed a second ago was the integral from 0 to 3 of the function x squared. Actually, I guess it was technically the integral from 0 to 3 of the function t squared, because our input variable there was dt. When we write this down, this is tall, skinny s is the integral symbol. It evolved from people, this sigma was a Greek, so a capital Greek S is a sigma, is the notation people use for adding things up. And at some point in the 1600s, people writing that fast, it became this tall, skinny S thing. If I want to write a very fancy version, it would be like that. Something like that. Is a very good penmanship version. Most people write it kind of wider and more S-like. The A and the B are the bounds of integration. Those are specifying what is the interval that you're evaluating that function over. F of x is the thing you're integrating. Which is called the integrand. And then the dx is, I don't know a name for this. The integral thing has a really weird notation going on. This dx is kind of like a closed parenthesis that doesn't make any sense. The thing that it's representing is it's sort of a reminder that the things we add up aren't the function values themselves, it's the function values multiplied by the length of the interval. We use delta x as the name for what is the length of the subinterval when we compute a Riemann sum, and somehow when you go from Riemann sum to integral, the delta x turns into a dx. The same way that when we write dy dx, the dx is kind of like a small number that you divide by, but isn't really a small number you divide by. In the integral symbol, the dx is kind of a number that you multiply by, but isn't really a number that you multiply by. And it's really serving more like a closed parenthesis. When we write the integral from 1 to 3 of x squared dx, this makes sense? If you wrote it without the dx, though, this is meaningless. And if you ever see me write something like that, it just means I forgot to write the dx, which people do a lot. Like, people forget about the dx because it doesn't really do anything. What it's really acting like, though, is when I write the integral from 1 to 3 of x squared minus 4x plus 7 dx. What it's sort of serving as is this is the start of the integral, and this is the end of the integral, and everything in between is the thing you're integrating. So it's sort of like a closed parenthesis in that sense. The way I've written it here, some people will consider wrong, because the dx isn't just like a closed parenthesis, the way I described it like 1 second ago, but it's kind of like a parenthesis that you multiply by. Like, we're kind of multiplying the thing by the dx. So some teachers will say there should be a parenthesis there to indicate that it's all getting multiplied by the dx. Without the parenthesis, it doesn't mean anything, though. So, like, there's no bad other interpretation. These parentheses aren't important because it doesn't mean anything without the parentheses there, or something like that. And I think everybody understands what you mean if you write this without the dx there. The dx is kind of like a parenthesis, but it's like a parenthesis that you multiply by. By that, I mean when we write the integral from 1 to 3 of, say, 1 over x dx, people will sometimes write this as, they'll say, well, you're multiplying a thing by a dx. To multiply by a fraction, you stick that on top of a fraction. So people will write this as dx over x is a fine thing to write, but it sort of messes up my thing saying that it's a parenthesis, because if I have parenthesis 1/3 close parenthesis, I wouldn't rewrite that as close parenthesis over 3. That doesn't make any sense. So the dx kind of is a thing that doesn't make sense. It's a weird tradition in math that it's hard to wrap your head around. But let's try an example. Let's estimate the integral from, let's make it 1 to 5, 1 over x squared dx with a midpoint Riemann sum using, should we make n equals 6? 6 is a hassle. Well, let's just make it a hassle using n equals 6. So we're going to cut the interval. So we're using n equals 6. The thing that this is telling us is we need to cut into 6 pieces. This is what it means when they say an n value. What is getting cut into 6 pieces? We're looking at the integral from 1 to 5. This is an interval of length 4. I need to cut that into 6 equal pieces. Cutting that into 6 equal pieces will give subintervals of length delta x equals 4 divided by 6 is 2/3. So our subintervals should have length 2/3 each. It's worth noticing, this instruction said cut it into 6 pieces. It could have, instead of telling us n equals 6, it could have told us delta x equals 2/3. Either of those gives you the same amount of information. I can either tell you how many pieces to cut it into or how big should the little pieces be. Either of those is enough to figure out the problem. Usually it'll give you one and not the other. You gotta figure out the missing piece from the piece you have. Each piece has length 2/3. We're cutting 1 to 5 into 6 pieces of length 2/3, so that'll be from 1 to 1 and 2/3 is, what is 1 and 2/3? That's 5/3. From 5/3 to 7/3, from 7/3 to 9/3, from 9/3 to 11/3, from 11/3 to 13/3, from 13/3 to 15/3, which is 5. Maybe I should write that 1 as a 3/3 at the start. Measuring everything in thirds makes it easier to write out these intervals. 3/3.